Hello, welcome to Fundamentals of Acoustics. Today is the second day of the 9th week of this course. Yesterday we started discussion on modeling and design of expansion type of mufflers, which is another name for which is reactive mufflers. And what we had shown yesterday is that if we have a muffler with a topology like here as shown in this figure, then the relations between pressure in section 3 and section 2 and section 2 and section 1 and similar relations for density are given here. So, with this understanding, now let us calculate the density in each of these sections. So, not density, so density we have already calculated. So, next we will do is compute velocity of sound. So, we know that C equals gamma overall pressure divided by overall density, and then we have to take the square root of this. So, we can write that C3, which is the velocity of sound in the third section, equals gamma times P3 divided by rho 3. And what is P3? This is equal to gamma P2 over rho 2, and I have to multiply it by m on both sides, because P2 is P3 is equal to rho 2 m and rho 3 is also equal to rho 2 m. So, essentially what is happening is that density is increasing and also the pressure is increasing in the middle in the third section. So, this means that C3 is equal to C2. C3 is equal to C2. Similarly, we can show that C1 is equal to C2. So, essentially what that means is that C1 equals C2 equals C3. So, the speed of sound throughout the muffler, it does not change, and the reason it is not changing is that wherever the pressure goes up, the density of also air goes up. So, this ratio P over rho remains constant. Okay. So, pressure is not changing, rho is changing, but the ratio does not change, and because of that the speed of sound does not change throughout the muffler. So, C1 is equal to, so now what we will do is we will compute R23. So, R23 is equal to rho 3 C3 over rho 2 C2, and we know that C2 is equal to C3. So, they will cancel out, C2 and C3 cancel out, and rho 3 and rho 2, the ratio of rho 3 and rho 2 is m. The next parameter we are going to compute is R12, and that is equal to rho 2 C2 divided by rho 1 C1, and once again C2 equals C1. So, I am going to cancel them out, and the ratio of rho 2 and rho 1 is 1 over m. And finally, R13 equals 1. So, we will plug these relationships into our expression for T, which is here, and we will compute the transmission coefficient. So, T equals, so I will first write that expression again and then we will plug those values. So, it is equal to 4 R13 divided by R13 plus 1 whole square 1 minus R23 minus 1 R23 square minus 1 times R12 square minus 1 divided by R13 plus 1 whole square sine square K2L. Okay. Now, R13, what is R13? We have calculated that it is equal to 1, R23 is equal to m, and R12 is equal to 1 over m. So, we will make these replacements in the relation, and what we get is that transmission coefficient equals. So, this 4 R13 divided by R13 plus 1 whole square, they cancel out, because 4 R13 is 4 and R13 plus 1 whole square is 4 also. So, this is 1 divided by 1 minus m square minus 1 times 1 over m square minus 1 divided by 4 sine square k2l, and this I can write it as 1 over 1 minus m square minus 1 divided by 1 minus m square by 4 m square sine square k2l. Okay. So, m square minus 1 times 1 minus m square is same as m square minus 1 the whole thing square times minus 1. So, this I can write it as 1 minus m square minus 1 whole square sine square k2l divided by 4 m square, and because I made m square minus 1 whole square, I have to change this negative sign to positive, and finally we bring it into its final form. So, this is equal to 1 over 1 plus m minus 1 by m square, okay, by 4 sine square k2l. So, that is my transmission coefficient. Now, what we are really interested in is not how much sound is getting out of the muffler, but how much sound is getting reflected back. So, what we are interested is not the transmission coefficient, but transmission loss. So, transmission loss we write it as TL, and this we calculate on a log scale. So, because T relates to the intensity of sound which is getting transmitted, if I take its 10 log, and if T is high, if T is large, then transmission loss will be less, and if T is large, then transmission loss will be high. And so if T is high, then TL will be low, if T is low, then TL will be high. So, to do that, we take 1 over T. Okay. So, this is equal to 10 log 10 of 1 plus m minus 1 by m whole square sine square k2l by 4. So, this is our final expression. So, this is transmission loss. And we would want that this transmission loss for a muffler should be as high as possible. So, what we see is that this transmission loss depends on two parameters. One is this parameter m minus 1 over m. If this m minus 1 over m parameter is large, then transmission loss is going to be large. The second parameter is sin square K2L. If sin square K2L is large, then transmission loss will be large, otherwise it will be small. So, what we do is we state, we can say that TL will be maximum for a given value of m. When is it going to be maximum? When sin square K2L equals 1, because that is the maximum possible value, which means, so this means K2L equals pi over 2 radians, right. So, this implies, so it implies that L is equal to pi over 2 K2, L equals pi over 2 K2, and K2 equals 2 pi over lambda. And what is lambda? It is equal to C divided by F, okay. And this is equal to what is 2 pi F? It is equal to omega over C. It is equal to omega over C. We will do some math. So, typically when we, so let us say that we want to reduce the sound coming from an IC engine which is connected to a car. So, in cars most of the time the engine runs, so what it runs between what? It runs between 1500 and 4000 RPM, okay. So, 1500 RPM corresponds to 25 hertz and this 4000 RPM corresponds to 67 hertz. So, what does that mean? That our silencer or muffler should work in the limit 25 to 67 hertz, okay. So, we have to design our muffler in such a way that it reduces the sound between 25 hertz and 67 hertz. Now, even though our audible sound range is from 20 hertz to 20,000 hertz, most of us can barely hear 20 hertz sound, okay. We really start listening sound above 40 hertz or so. So, so I will reduce this frequency further. So, since not much sound is heard below 40 hertz, working range of muffler should be 40 to 67 hertz, okay. So, at 40 hertz, at 40 hertz, what do we do? We compute L using this relationship and we find that L equals 1.37 meters. Okay. How do we compute it? I first compute K2, which is omega over C, and then divide pi over 2 by K2. Okay. And at 67 hertz, L is equal to 0.82 meters. So, this is assuming C is equal to 345 meters per second. So, what does that mean? What that means is that if I have a silencer of this type, then this parameter L should be, if I want to kill 40 hertz sound very effectively, then the length of this parameter, the value of this parameter L should be 1.37 meters. And if it shifts away from 1.37 meters, sound will get reduced, but it will not be that effective. If I want the design to be such that 67 hertz sound is reduced, which corresponds to engine running at 4000 rpm, then L should be 0.82 meters. Okay. So, this is the conclusion for today's lecture. Tomorrow we will continue this discussion on mufflers, and we will learn more about this particular relation which we have developed, and we will also discuss somewhat about dissipative mufflers. So, with that, have a great day, and we will meet once again tomorrow. Thank you.